and then what I'm going to go on to try to do is convince you guys to read research papers, and we'll talk a little bit about why you would want to do that and how to approach a research paper. And then the second half of class, we'll apply our newfound enthusiasm and skills to looking at RAID, which is something that fits in with disks. So again, to remind you, in the past, we've done the research paper reading a little bit later in the semester. I don't know why that's way up there. And this year, we're sort of going to start to do this now, and then we'll interleave it with some other topics that we cover throughout the semester. So the reason we're doing this today is because we're pretty much done talking about file systems, and so RAID fits in here nicely, okay? Not much to say. Do the assignment. Right now, the maximum score when I checked earlier was 69 out of 100. So, you know, you guys have more progress to make. OK, so the first question here is, so I started writing this lecture, and I was thinking, well, I'll just talk about how to read a research paper. But I thought I would actually back up a little bit and actually try to motivate the problem, right? Because you know, it's not clear to me that all of you actually want to grow up to be just like me, right? I know you might want to be like mainly like me, probably better looking, make more money, whatever. But you know, so you know, this is part of my job. This is something that as a researcher I enjoy doing. But again, I'm not going to be presumptuous and assume that you guys want to do the same thing. So why read a research paper? So I mean, the main reason is because it's cool. Researchers have some really neat ideas about how to improve systems. And regardless, you know, what I discover when I read papers is, regardless of the projects I'm working on or the code I'm writing or the approaches that I'm taking to things, seeing how other people have solved problems is a great way to get your own creative juices flowing in terms of solving some of your own issues and addressing the code that you're trying to write. Because I'm assuming many of you guys will go on to be programmers and developers, and you'll be building systems and solving problems. And looking at how other people do things is a good way to get some ideas. And today, when we talk about RAID, you guys will see that the big idea behind RAID is something that I would say has sort of spread and has really influenced how we build lots of different types of systems, right? Not just disk. So RAID is technically this crufty paper about disks from many, many years ago. But in reality, the influence of RAID has been really enormous. And RAID-like ideas are used in a lot of different types of systems. So the second reason is, you know, and so the other thing you might think is, well, you know, who cares about academic research on computer systems? They're not doing anything interesting anyway. You know, what I really care about is Google and Facebook and Microsoft, and those guys are building real systems that are out there and used by real users. And to some degree, that's true. But what you find out, I mean, if you guys go look at top systems research conferences, there are a bazillion papers, particularly from Microsoft. Microsoft is a very active research lab, and they publish all sorts of things. And frequently, also, when you start to look at production systems like Google and Facebook and some of the things they do, really the only way you're going to get inside their heads is to look at some of the things they publish, unless you go and work there, in which case you know everything. But if you don't work there and you want to look at how they handle certain types of problems, particularly the problems that go along with providing the services they provide, looking at the things that they publish is a good way to do this. And in a few weeks, we'll come back and we'll look at the Google File System as an example of a paper about a production system that's in use at Google. Or maybe it's been superseded by something else, but at a certain point it was. And then the last reason, of course, is that even when you're talking about open source projects, reading the code is typically a really bad way to get a sense of some of the overarching design principles that went into things, right? You know, so, and then the other question is, you know, why do we keep doing research? You might think computers are fine the way they are, right? I mean, how many people think that? How many people pretty much think they would be happy if computers never changed, if they just stayed the same forever? You've got all the computing you want. Anybody? Well, it's good. I guess you guys are computer scientists, so I'm hoping that there's no one like, yeah, I just want to maintain legacy systems. You know, that's my dream in life, right? I just want to keep the things that are already working, right? Help them to keep working. Yeah, so you know, and even if you sort of ignore what some people call the feature factory, which is, you know, potentially a problem, and maybe there are new features and new things out there that we don't really need, and on any level, there's still a lot of new opportunities that are driven by new hardware capabilities and for other reasons, right? And so a lot of what happens in the world is stuff changes. Things change, new technologies emerge, and people that build computer systems try to figure out how to take advantage of them to fix problems with old systems, or in certain cases, take advantage of them to develop new capabilities. So, you know, in a time period that you guys have been alive, think about the last 10 years, what would you guys describe as some of the significant technology trends? So things that have changed, you know, new forces that are changing the way computer systems are built. I mean, you guys have experienced it in your life, yeah. Okay, I hadn't thought of that one. Yeah, virtual reality, virtual worlds. You know, people, and, you know, and I would sort of connect that with online gaming, and there's a lot of, you know, work in that area. What else? Yeah, Josh. Yeah, a lot of work on mobile, right? There's a lot of people out there in the world that have mobile devices. And particularly in developing countries, in a lot of cases, this is the first time that people have had access to the internet. You guys are lucky to be in this country where you've had these big fat devices that have been giving you access to the internet for many years. But in poorer countries, a lot of times the first time people get a phone is the first time they access the internet. So that's pretty cool. What else? Yeah. Cloud computing, there we go, right? You know, it's actually more than a buzzword. It's a real thing. But yeah, certainly commodity computing, all of these huge data centers. I mean, again, I said this before, but I mean, you guys have access to more computing power today than you did yesterday, and today than anyone else has in the history of the world. And that just keeps going up and up and up. And I think it'll be exciting to see what we do with all this power. We've built all this stuff. We've collected all this data. But I think we're just getting to the point now where we're actually starting to make some use of it. So what else? A couple other things. These are good. These are good. What other sort of hardware trends have taken place? Yeah. Sure, GPUs. There's a lot of focus on GPU computing for parallel processing. That's a great thing. So here are the same things I put down. So the end of Moore's law scaling. We got to a point where we couldn't make things faster by making transistors smaller anymore. It just doesn't work. There are these thermal constraints and other power problems that causes. And so you might have noticed that around that same time, when the clock speed on your computers stopped going up astronomically, the number of cores on your computers started to increase. So this is a huge shift, right? And it also has a lot of impact in terms of how we design new systems and new languages. You guys need to know how to use concurrency and exploit parallelism as programmers in the future, because even your smartphone now has several cores. How do you put those to work? Flash, right? Flash, cool new technology, lots of work on integrating this into our existing storage stack and making use of its features. Cloud computing, somebody already said. Smartphones, battery-powered devices are everywhere. A lot of users now interact with multiple devices. So they have applications that they want to work seamlessly across their tablet, their desktop, their laptop, their smartphone, their other smartphone. And you know, the Internet of Things, smart dust if you buy that stuff, and I would also say fast, high-speed connectivity everywhere, right? That's a really new thing, and that's a real game changer for how computer systems are built. So this is all the stuff that's going to keep driving these areas forward for the next decade, and 10 years from now, there'll be other things on this list. But this is why we keep working on this stuff, is because the world keeps changing. And then, yeah, there's a good zillion things happening. Right. Okay, so now let's talk about how you actually approach research papers. And I'm not going to lie, research papers can be dry, dull, boring, uninteresting, etc. And I am not guaranteeing that if you go out there in the internet and you find some sort of academic or industry research paper and try to read it, you're going to have a positive experience. Part of knowing how to read a research paper is knowing how to not read a research paper that's terrible and figuring that out as soon as possible, right? So, you know, don't, and so part of it is, okay, so let's start with this. So you guys are ready to read these papers. I will declare it today going forward. With the background that you've acquired in this course, you guys can start to sit down with certain type of research papers and understand them. I'm not, you know, there's going to be some terminology here and there that you guys won't get, but from a high level, I think you guys are ready to digest some of these ideas. One thing that makes this significantly easier is if you guys read good papers. So I have graduate students sometimes I work with, and before they really understand sort of where to go to find good papers, they end up reading these really terrible things they found on Google. And that's a real great way to kill your appetite for reading research papers. I mean, it's hard to read papers even from top-tier conferences because there's usually a bit of complexity to what they've done. But if you're reading a bad paper about something uninteresting and an idea that doesn't really even work very well, it's going to be bad. You're not going to like that. So one of, and I think the other mistake people typically make when they read research papers is they think they have to read the paper, right? They sit down with this 14-page thing, and they start on page 1 in the upper left, and they start reading, and it's sort of like a novel. They think, oh, I've got to keep reading here. I can't skip this part. No, no, no. Don't be afraid to skim forward, skip things that don't look interesting. Look at the pictures first. I'm totally serious. There are graphs in papers. Sometimes you can just look at those graphs and get a sense of what the paper is about. Don't worry about, you know, skipping whole sections of the paper. If you get confused, just go on or give up. You know, you don't read these like a book, right? You read them sort of in a variety of different levels. If you're really curious, if you decided that the paper is cool and you're really curious about it, then you have to slow down and actually read for the details, because typically there are a lot of details in the paper. But you certainly don't have to read it that way on a first pass. When I sit down with a research paper, I would guess I probably spend on average maybe 10 or 15 minutes reading a research paper. And that's because I read a couple pages, I have some idea of what they're doing, I look at the results and try to convince myself that it worked or it didn't, and then I'm done. I don't really care how they built it, right? Unless I'm going to try to build the same thing, in which case I'm usually not, because they did it already, right? It's too late. So the next couple things we're going to talk about are where things get published, the kinds of papers, and the parts of a paper. So these are really important understanding to getting a sense of what the landscape is like, and these will help you read research papers and digest them. Okay, so places where papers get published. So in general, there are 3 kinds of research paper in computer systems. Is that a question? Okay. There are what are called workshop papers. And workshop papers are actually frequently really fun to read. And the reason they're really fun to read is they're short, like 5 pages long. And it's almost like they took the longer paper and they just boiled it down to the parts that are really interesting, provocative, and exciting. And that's the workshop paper, right? So it's small. There's not enough room to fully describe a complete system. And so what the paper does is it just tries to make an argument, get you excited about something. Usually they don't frequently you can write a workshop paper without building a real system. That's why people like to write them, right? So here's an example. This is a paper by Margot Seltzer, who you know, that was published at HotOS, which is a workshop on hot topics in operating systems that gets held every other year. Apparently, there's only hot topics in operating systems in odd years, and even years there's just cold topics, so they don't hold the workshop. And you can see the title, right? Hierarchical file systems are dead. It's pretty provocative. We've been using hierarchical file systems for decades. And these guys are arguing that they're dead. We're not going to use them anymore. And if you look at the paper, that's the argument they make. Is there a real system behind this paper? No. There's just an argument that it's time to move away from the way that file systems have been organizing information for 30 or 40 years. And so that's a pretty interesting argument. And this is a pretty interesting paper. So the real sort of place to look if you want to read about full systems are conference papers. These are longer. They're like dozen pages, 14 pages, 16 pages. They're designed to be long enough to present an entire result. And usually they include an evaluation of a system, a design, some arguments about why it's important. Here's an example. It's called the scalable commutativity rule. I wish I could pronounce that word. These guys are the sort of top tier guys at MIT and Harvard that do work in computer systems. And this was the paper behind one of the midterm questions that you guys tried to answer. So this is a very cool paper. And then finally, there are journal papers. And all I would say about journal papers is I would just not read them if I could get away with it. Because in computer systems, journal papers are usually longer versions of conference papers. And to be honest, the stuff that got left out of the conference paper is not interesting. And so don't slog through it if you don't have to. Find the conference paper and read that first. And if there's a workshop paper, find the workshop paper and read that first. Because usually you can get the idea. OK. So anyway, we don't need to look at these. There's a longer conference paper. OK, I don't know why these are actually in here. Come on, keep going. No, don't die on me. All right. So now we'll talk about kinds of papers. I don't know. So those are where papers get published. Then when you start to look at what papers try to do, right, there's a couple of things. The most exciting papers to read are big idea papers. And then there's the other papers that have an idea that maybe doesn't turn out to be so big. And big idea papers typically present a new way of solving a problem, an important problem, and a novel way of addressing it. You have problem papers. So problem papers are different than big idea papers, where problem papers try to convince you that there is a new problem that we should be solving, that there's something that's important to how computer systems are designed that people are not working on. In order to write a good problem paper, you usually have to have some kind of solution, but it doesn't necessarily have to be a perfect solution. Part of your goal is to convince people to work on this problem. This is a problem we should be working on, and here's a preliminary solution. Data papers, so papers that present some type of novel analysis of data sets. And these are really important for systems research because a lot of what we do is driven by understanding how real systems work. And so if you have data about how real systems work and you can use that data to make a new point about how we should build systems, that is exciting. New technology papers. So in this case, I have some new doohickey. There's some piece of hardware out there, and I'm trying to figure out how to get it to work. So for example, in the mobile systems community recently, there's been a lot of interest in new networking technologies. So networking with things other than RF frequency in the unlicensed spectrum bands. So for example, can I point two smartphones at each other and have them communicate through visible light? So one screen is flashing images at the other one, which is recording it with its camera and using that to transfer data. There is work on using sound waves to transfer data, for example. So these are examples of people trying to either use a new technology or use an old technology in a new way to provide some new feature. And then finally, and the hierarchical file systems are dead paper is kind of an example of this. There are what I would call wrong way papers. And the wrong way, there's a lot of workshop papers that fall into this category where they're trying to convince you the way that the community has been working on this or thinking about this is totally wrong. And we should all change directions. And these are fun papers to write. It's a high bar, right? Because you're trying to convince a bunch of smart people that they are totally misguided. And most people in any research field typically tend to think that they're right about most things. So trying to talk them into being wrong about something is not necessarily an easy task. OK. So when you start looking at research papers, it's really important to sort of be able to break them into their parts and understand what's interesting and where to look. And so this is sort of a taxonomy of the parts of a research paper. Now, there's no requirement that people write research papers organized in this way. And so you find lots of different variations, but these are what I would consider to be some of the standard elements. So the first group fall into the category of why you should read this paper. And this includes things like the abstract. So in many cases, the abstract is one of the best things to read about the paper. Sometimes it's the best part of the paper. It's short, it's concise, and it's trying to get you to read the rest of the paper. So the goal of the abstract is I read the abstract and I say, you know what, I would really love to read the rest of this paper. And so the abstract usually is a nice overview of the contents of the paper. And sometimes that's really all you need to read. Or sometimes by reading the abstract, it allows you to develop a strategy for how you're going to read the rest of the paper. The introduction is usually just a longer version of the abstract, but it contains a lot more information. So the introduction is the first thing people tend to read about a paper, and the introduction is supposed to bring you into the headspace that the paper wants you to be in. So why is this an important problem? Why is this solution so awesome? Why should you read this? Why are there general arguments about computer systems that are embedded in this paper? What have we done? Some preview of the results that we're going to show you. In a lot of cases now, people have gotten to the point where they have a section in the introduction that says, here are the contributions of this paper. It's fantastic. You can read that and say, OK, either I care about the rest of this or I don't, and it goes into the trash. And then usually the introduction gives you some sense of how the rest of the paper is going to unfold. A lot of people will tell you that when they try to write papers, the introduction is the make or break section. If you're not excited about the paper after you read the introduction, very few people are going to read the paper, and if you're reviewing the paper, you're probably not going to like the paper very much. So the introduction really has a lot of work to do. A lot of papers have an additional section with more motivation, maybe more data, more detailed arguments about why this is an important problem, why this is an important solution, why this data that I'm about to analyze is important, or whatever. OK, so the next part are the what we did, what we built, how it works, parts of the paper. And frequently there's a design section, which gives you a high-level overview of the design of the system. And again, there's no standard here for how to write these. If you guys read the RAID paper, you're probably wondering where were all these sections in the RAID paper, because the RAID paper has few to none of these. But they're actually there. They're just called different things. An implementation section might have a little bit more details about how they did it. This is one of the sections of the paper that's very skippable unless you really care about the details of getting whatever they did to work on whatever version of Linux they used to get it to work. Usually you can just sort of assume, OK, they got it to work. On I go to looking at how well it worked. So related work is also, I think, an important part of what we did, because it gives you a sense of how this project is different than other things. And when you start reading research papers, it's really important to look at this section because you don't have a lot of context for what else is out there. And so you may not know about most of the systems that do similar things, and a good related work section will not only introduce those systems to you, but will tell you, here's why we're solving a problem that this system didn't solve, or here's why our system is better than this system or does things that this other system doesn't do properly. So for data analysis papers, which we'll talk about in a second, or which we talked about earlier, most of the paper is really spent talking about how we analyze the data and the results from the data. Because you don't build a system when you write a data analysis paper, there's not necessarily an evaluation, which we'll get to next. So the final part is a part of the paper that concerns, did it work? How well did it work? And this is where you typically find graphs. So the design section, you'll typically find diagrams. It's almost, for years, I think every systems paper had to have some sort of architecture diagram with blocks and names and arrows pointing at each other. Those aren't always super helpful, but they sort of had to be there. The implementation is where, the evaluation is where you have graphs that are supposed to go up and to the right, various figures that try to convince you that this system worked. And so this is sort of how you can identify these visually if you're just scanning through a paper. All right, so any questions about how to do this? And I would encourage you guys, particularly when we get to, so the RAID paper is a little weird as a starting point. It's a technical report. It's a little bit longer. Yeah, Jill. I will, if people are interested, I will address that in a separate lecture. That's a hard question. But one thing I would say actually is that one of the ways to come up with your own ideas is to read other people's ideas. when I started as a graduate student, I didn't like reading papers very much. And I still would say it's not my favorite thing to do. I've gotten better at it because I don't have to spend as much time reading a paper. But the thing that's paradoxical is that you might think, oh, I don't want to read about how other people did things because that will just crush my own creativity. So it turns out that's actually not, at least in my experience, that's not true. And in fact, it's the opposite. Reading about other people's ideas gives you, sort of gets this stuff into your brain where it circulates and then allows you to come up with new approaches to things. So I would say one of the ways, if not the only way, is to read papers and think about how real systems are built. It's a good question. Any other questions about how to approach research, reading research papers? All right, perfect. OK, so now let's talk about RAID. So what kind of, going back to our list of kind of papers, now this is a technical report, so it's sort of like a journal paper. It might have had details that wouldn't have been in a shorter version. But what kind of paper is this? Is this a data analysis paper? Yeah, so this is a big idea paper. How do we know it's big? You can buy it, right? I mean, the number of research papers where you can take that paper and go to the store and say, I want this, is very small. And this also, of course, gave birth to a huge industry devoted to making these things. And I would argue that the core idea here, like I mentioned before, has really inspired how we design large-scale systems in a lot of cool ways. OK, so what is the big idea in this paper? And my hint to you is that don't say anything, don't use the word disk. Don't use the word file system. Yeah? Yeah, I mean, that's half of it, right? So I can use multiple cheap things to produce something that performs better than an expensive thing. So if you look at some of the tables they have, and this is a fantastic paper. I don't know, maybe they might have drawn those tables with a ruler or something, right? I mean, this is far before the days where we had these nice tools to generate graphs and tables. But the argument here is, I could go out and I could buy this. What's the name of it? It's the Super Eagle, right? The Fujitsu Super Eagle. It's an awesome name for a hard drive, by the way. I don't know what happens after the Super Eagle, right? The even more Super Eagle. So you know, the argument that Patterson is making is I could buy the Fujitsu Super Eagle, which costs, for the purpose of our discussion, $1 million. Or I could buy 10 hard drives that cost $10,000 each. And the goal is to use these cheap commodity components, working together, several of them, to produce a system that outperforms the big, expensive thing. So what other places do we see this idea applied? Give me some examples of where we see this. Yeah. Yeah, OK, so that's fair enough, right? I mean, you know, graphics cards, right? I can chain multiple graphics cards together to get better graphics performance than I could get from one super expensive graphic card. That's a good application. Where else? Yeah. Yeah, I mean, Google, right? Google search. A lot of Google products work this way. When Google started out, they were filling their data centers with commodity computers that they were bought from Dell. True story. Now, of course, they're big and they have their own rack servers that are designed to their specifications. But Google hasn't created this incredibly powerful cloud computer by purchasing a really expensive supercomputer. They didn't go out and buy when they wanted to support search, they didn't say, let's go buy a Cray supercomputer and pay, I don't know, however much it costs. They said, no, we're going to buy thousands and thousands and thousands of Dell commodity computers. And we will figure out a way to get them to work together to do what we want. Where else? Yeah. Yeah, sure, multi-core, right? I mean, you know, can we make faster and faster and faster single-core processors? Yeah. But I mean, do you have room in your pocket for a heat sink that's 2 feet tall? No, right? So it's not that we can't do it. It's just it's a better idea to start using multiple cores rather than one single super, super fast core, right? So I think we got most of the ones. Crowdsourcing is another case, right? Things like Mechanical Turk. I could write a really sophisticated algorithm to do this, or I could just hire a bunch of people and pay them $1 each, right? Sometimes the cheap commodity parts, in this case, that are human beings, outperform the extremely sophisticated algorithm. OK, so what's the? I mean, this sounds like a fantastic idea. We're going to replace big, expensive things with a less expensive combination of smaller, cheaper things. What is the problem? And this problem really applies to a lot of these examples that we've come up with. Not all of them, but a lot of them. What happens when I start getting bunches of things? Stuff fails. So since we started this, you know, our conversation today, I don't know, maybe 50 hard drives in Google data centers have failed. They're probably, actually, it might be more than that. They might be failing every time I say the word write. So more cheaper things. I mean, the cheaper things are going to fail anyway, but because I have so many of them, I mean, if you think about how many computers Google has in their data center and think that those computers last 2 years, they're failing all the time. It's just normal. And so we have to make a plan to deal with failure. Oh, whoops. OK, so this is the second half of this slide, right, which is that the cheap things fail a lot more quickly. The problem that the RAID paper identifies is, and this is one of these famous introductions in computer systems papers, where it's just extremely nicely laid out, and you get to a certain point in the paper and you think, mankind cannot go on if we don't solve this problem. You know, the pending I/O crisis, right? I mean, we're going to have to leave Earth if we don't solve this. We're going to have to build one of these interstellar things and explore other galaxies if we don't solve the pending I/O crisis. It's that critical. Because the CPU is getting so much faster, and memory is getting so much faster, and all that stuff's being driven by Moore's law back when this paper was written, except the disk is just not getting faster. And so, you know, the I/O crisis. We need innovation to avoid an I/O crisis. Now, the problem with RAID, as I just pointed out, is that a lot of things, the more things you have, the more quickly those things fail. And remember, we're also using cheap stuff, which probably fails faster than the expensive stuff. Maybe not as much faster as you would expect. I could probably spend 10 times more to get a hard drive that might last twice as long. But the cheap stuff is going to fail. OK, so here's it's going to be hard to see this, so I'm glad I wrote slides about it. So this is the, going to get it to go that way. Come on. So, well, anyway. Ah, beautiful. OK. So, and again, I mean, this is kind of a, so here is memory is getting faster, right? The CPU is getting faster. The pending I/O crisis. This is just a fantastic section in the paper. It has its own section. It's 2 paragraphs long, right? And we will actually come back in a couple of weeks and talk about Amdahl's law. But there's a very convincing statement here where if computers get 10 times faster and the disk doesn't improve, then we're going to lose half of that speed up. The effective speed up will be 5 times. If the memory and CPU get 10 times faster, I/O doesn't improve, the computer will only seem 5 times as fast. So we have this potential to lose an enormous amount of speed up. So here's our solution. The solution is a arrays of inexpensive disks. And they do a nice job, and you can ignore most of these numbers, of comparing between the, I think this is the, let's see here, so price per megabyte. So this is my expensive drive. This is the $20 to $17 per megabyte for, I guess that's the Fujitsu Super Eagle, the M2361A. And then I have these cheaper, I have a cheaper drive. So I have this one here, which is $10 to $7, and I also have this IBM 3380. So the point here, now you can actually see the Fujitsu, for whatever reason, has, this is MTTF rated, mean time to failure. How long does the device last? It turns out the Fujitsu actually doesn't last any longer than the cheaper drives, which is interesting. And then there's details about this, but you can see that let's see here. So when you look at the performance, the Fujitsu is a more performant drive, but it is also considerably more expensive. These are a little bit dated, so let's go forward and start to look at RAID. So we'll talk about the 5 RAID levels, all 5 of them, because one of the things this paper does very effectively is it tells a story. So I don't know how, if you had to ask, I doubt that Patterson invented these in the order in which they appear in the paper. I think maybe they invented RAID 5 and worked backwards. But the paper does a really nice job of showing you where all the trade-offs are at each level. So let's start with RAID 1. We will come back to the mythical RAID 0 at the end. Let's talk about RAID 1. So what is RAID 1? What is RAID 1 reduced to? In all these cases, I'm imagining I have 2 or 3 drives. So in RAID 1, I've got 2 disks. What do I do with them? What's that? Yeah, so RAID 1 is also known as mirroring. In RAID 1, you can imagine I have 2 identical drives. Whenever I do a write to the file system, from the file system's perspective, RAID 1 looks like 1 drive, but there's another drive there. So RAID 1 looks identical to just having 1 drive, but I have an entire drive sitting there as well. And what I do is I keep that second drive up to date with the first drive by any time there's a write operation, that write hits both drives. So this is very simple to implement. Whenever I get a block write, I send that block write to both disks at the same time. And now, when can that write complete? So to write a block to a RAID 1 array, when is that write allowed to complete? So I'm going to write all data to both drives. And so what do I have to wait for? Yeah. Yeah, so I have to wait for both drives to finish. And it turns out that both drives may not have the same performance for writes. And that's because of how I do reads. So let me ask you a question. Do I have to read the data for both drives? No, because it's identical. So for reads, what I can do is I can actually load balance the reads between the drives. So for example, I could send half the reads to drive 1 and half the reads to drive 2, and that's totally safe, as long as the write's always complete. So so let's look at the different, so we're going to assume for the purposes of this discussion that we can maintain fault tolerance for this system, and we'll come back to how we do that at the end. So what we're going to focus on here as we go incrementally through the RAID levels is how performance and capacity change. So performance for this system, is there an improvement here over using a single disk? So the answer is maybe. It's better for reads. So for reads, I can get twice the bandwidth because I'm using both disks in parallel. For writes, I actually might slow down a little bit depending on where the heads are. So the reads are definitely going to improve. What about the capacity? So here's the problem. you just spent you just spent money and got 2 terabyte drives. How much storage space do you have if you use RAID 1? 1, right? Does that make sense? So as we go up through the RAID levels, we're going to improve both the performance and the capacity compared with RAID 1. The capacity here is clearly the biggest problem, right? I don't want to have to spend twice as much to get a little bit improved performance and redundancy. That's not, I can do better than that. Okay. So what we do for RAID 2 is RAID 2 introduces some of the core concepts that underlie other parts of the RAID system. And you can imagine, I think RAID 2 through 5, you need at minimum 3 drives. But these examples show more than this. So what I do with RAID 2 is, you imagine I have a block of data. That block, from the disk perspective, maybe has 256 bytes. I write bytes of that to consecutive drives. So this is called striping. I take the block and I stripe it across all the different drives on a per byte basis. So byte 0 goes to drive 0, byte 1 goes to drive 1, byte 2 goes to drive 2, and then maybe I go back to the first drive. In order to detect and recover from failures, and I was just listening in on the end of Steve's lecture, I use a type of error correcting code. It's called a Hamming code. Now, the Hamming code can actually do 2 things. There's enough information in it to detect which drive failed and to recover the error. So if any of these drives fails, I can use the extra information to not only pinpoint the drive that failed, but recover from the error. Now that requires some extra information. So you see here, for 4 bytes of data, I need 3 bytes of Hamming code. And that's true throughout the rest. So this would represent 4 times 4. This is 16 bytes of data. You'll see that it's been striped across all 4 drives. Now you'll notice that most reads and writes most realistically sized reads and writes are going to require all of the disks. Why is that? Yeah. Right, so I don't read bytes. I read blocks. So if I read a block of data, unless I have more than 256 disks, it's going to require every disk. Because here you can see, even just to read 5 bytes of data, even to read 4 bytes of data requires every disk. And because of how the data is laid out on disk, it means that any read or write has to touch all 4 drives, and writes may have to adjust the Hamming code as well. So from a capacity perspective, I've improved on RAID 1. I do not. So I have more, for RAID 1, I would have, I don't know, I mean half, I would mirror the drives together, and RAID 2 allows me to improve the capacity. So I'm not getting 50%, I'm getting a little bit more than that. The performance is pretty much the same. In fact, in a way it's worse than RAID 1 because the writes and reads both have to use every disk. So in general, every write and every read will have to touch every disk. And so the entire array of disks has to work together to satisfy every read or write. So this is not fantastic. In fact, it's a little bit worse than RAID 1 because remember, for RAID 1, I could do multiple reads from different disks at the same time. Here I can't do that. OK. RAID 3. So the key advantage to RAID 3, the key difference from RAID 2 is simple. In RAID 3, I assume that I can figure out which drive failed. Why? Remember, the Hamming code allowed me to tell you which drive failed. Why in RAID 3 have I decided I don't need that capability? Yeah. Yeah, drives just die, right? Drives don't lie, usually, right? I mean, a drive fails by just not working anymore. It doesn't fail by giving you incorrect bytes, typically. So the argument in the paper is that, look, drive controllers can detect drive failure. And again, in many cases, it's fail-stop behavior. It just stops working. It won't power on anymore. It's just they're clicking at you or whatever. So forget being able to identify the drive that failed. I don't care. I let the controller do that. This allows me to significantly reduce the amount of extra information I need to maintain to tolerate failures. So now I only need 1 bit of information. So if I have 3 bits of data, I need 1 extra bit, which is called a parity bit. The parity bit allows me to recover any lost bit regardless of which drive fails. And so now here what you can think is, here are my 3. So if I do this on a byte basis, I have bytes 1, 2, and 3, and this is my parity byte. So regardless of which disk fails, if disk 0, 1, or 2 fails, I can use the parity disk to recover the missing byte. So the advantage here is I've reduced, so remember with RAID 2 I needed 3 disks here. And here now I would only need 1. And I only need 1 regardless of how many other drives I have. Even if I added another disk here, I would still only need 1. I only need 1 parity byte. However, in many ways, this suffers from the same problems that RAID 2 had with respects to reads and writes. Reads and writes still require all of the drives. So reads have to hit all 3. Reads are going to require all 3 of these, and writes are going to require adjusting the parity byte as well. So this is still a problem. Yeah? Does it make things faster? No, because I'm not actually harnessing the parallelism. I have to move the heads in the same pattern. Right? So I actually, remember, the seek times are what dominate. So the transfer time, you're right, the transfer time's a little bit faster. But it's the seek times that dominate, and the seek patterns are identical. What I want to do is I want to allow the drives to work in parallel, so I'm transfer data from one while the other is seeking to another location. Right? But yeah, so this does improve slightly on the performance because you're right, I have less data to pick up once I get to the point on disk where I want to go. Right? But it doesn't allow me to run the disk in parallel and do seeks in parallel, which is what I wanted. So the capacity is improved over RAID 2. The performance is very similar. So now let's go to RAID 4. So the difference, and this is the level that always confuses me, but the difference is actually pretty straightforward. Instead of doing byte level striping, I do block level striping. So unfortunately, the diagram looks almost identical, except that Wikipedia decided to use different colors. But the difference here is that these are blocks. So it's a 256 byte block. So block 1, block 2, block 3. And this represents 16 bytes of data. This now represents 4 kilobytes of data. And I can do this, right? All it means is that each one of my parity bytes is now a parity block. It has all the parity information for all the bytes in the block. The nice thing about this is that reading a single block now only requires 1 disk. So if I want block A1, over here I would have to read all of these bytes and then a bunch of other stuff, right? So I definitely need all 3 drives. Here I just read it from disk 0. And now what's the problem here? So this is good for reads. Now I should be able to distribute the reads between the drives, which is what I want it to do. What about writes? Why does this fail for writes? I'm not quite there yet. I clearly have another level, right? So what's the problem with writes? It's actually on the slide. Yeah. Right, so the problem now is that my writes get bottlenecked on the parity disk. So any write to this array is going to write to one of the disks, 0, 1, 2, and disk 3. Always has to write to disk 3. And so, can you guys see what's coming here? What is the natural way to fix this problem? How do I lay out things? Yeah, so let's distribute. OK, sorry. So the performance of RAID 4 is improved for reads. RAID 5, block level striping, multiple parity disks. So now every disk stores some parity information. So you'll see here, these are blocks A1, A2, A3. This is my parity block for those blocks. This is block B1, B2, B3. Here's, sorry, B1, B2, B3. Here's my parity block for those blocks. And so what I did is I took all these parity blocks that were sitting on disk 3 and creating a bottleneck, and I've interleaved those parity blocks between the multiple drives. And this is RAID 5. I'm trying to think. Of the RAID levels, I think RAID 1 and RAID 5 are the most commonly used in practice. The rest are just purely for academic, of sort of academic interest. And so this now works very well, because now I've managed to improve my write performance. I'm still going to have to write to 2 disks, because I always have to update the parity information when I alter the data. But now those writes will be evenly distributed across the drive. OK. Any questions about these RAID levels before we talk about the fake RAID? Fake RAID. So this is a very, I think this is a very elegant idea, right? It's simple, but the paper is nice in how it walks through level by level. It talks about how things change and motivates the improvements. OK. So RAID 0, I just want to comment on this because people may have heard of it. So RAID 0 is not RAID. It has no redundancy at all. It essentially takes 2 disks and combines them together into one file system. The nice thing about it is the performance is awesome, because all of the reads and writes go to one of the disks. The capacity is fantastic. I get to use every byte I purchased. The redundancy is 0. So this is only for the brave. And in fact, this is worse than a single disk. Why? That's right. So you've doubled your probability of failure, right? But still, there are people that like to do this. They have other backup strategies. OK, so remember, so just covering redundancy quickly. So RAID is designed to tolerate the failure of 1 and potentially more disks. Once a disk goes down, once it's tolerated the max number of failures, if another disk fails, you can start losing data. And so what happens is when a disk goes down, someone's got to go in there and swap out a new disk. And RAID arrays actually can come with what are called hot swaps, which are disks that sit there and are ready to be moved into the array as needed. Or this can be done by a human being. All right, any questions on RAID? I know we're out of time. Anyway, it's a cool speed. Yeah, so one of the reasons why people like to use hot swap disks in RAID arrays is because if you take a blank disk and stick it into a RAID array, it can take days to rebuild, because it has to move and recover all the data that was on that drive, right? And so yeah, rebuilding arrays can take long periods of time, and it generates an enormous amount of disk activity. Yeah, it's a great point. OK, so on Monday, we're going to talk about different ways to design your operating system. And that will lead into next week a discussion of some other research papers. So I will see you guys on Monday.